Problem 9.32. ATMs must be stocked with enough cash to satisfy customers making withdrawals over an entire weekend. But if too much cash is kept unnecessarily in the ATMs, the bank is foregoing the opportunity of investing the money and earning interest. Of course, that's a little bit of background information to the problem. What we could also add to that is, of course, if you don't have enough cash in the ATM, that would cause concern for the customers. They might not be very happy with you if they went off to the ATM and weren't able to get cash because it had run out. So I suppose the background to this problem is just to think about the fact that there's a bit of a balance in terms of deciding how much to put into ATMs. You don't want to miss out on earning interest, so you don't want too much cash in them, but you want to make sure that you have enough because otherwise you will upset the customers. Now we're told, suppose that at a particular branch the population mean amount of money withdrawn from the ATM per customer transaction over the weekend is $160 with a population standard deviation of 30. So we've been given some information about our population mean and population standard deviation. If we now have a look at part A, we're told if a random sample of 36 customer transactions indicates that the sample mean withdrawal amount is $172, is there evidence to believe that the population mean withdrawal amount is no longer $160? And we're told to use a 5% level of significance. Now, way back in the introduction information, we were told about our population mean and population standard deviation. So at this point, we could have been talking about means, we could have been talking about standard deviation. The actual wording of part A tells us exactly what we've got to do in this question. We've got a random sample, so we've got a sample size of 36, we've got a sample mean of $172, and then the key information in terms of the wording of this question: is there evidence to believe that the population mean withdrawal amount is no longer $160? So we've been given some information about the population. You can think of it as a claim about the population mean. We want to know if there's evidence to believe that it's no longer that. So this is a hypothesis test. We've got a claim about the population. We've got a sample that we're going to use as evidence. And if you're in any doubt, the use a 5% level of significance confirms that we are going to be applying a hypothesis testing technique. Our focus is looking at the mean. Now, the only other thing I'll mention at this stage, so our claim is the population mean is 160. We have a population standard deviation sigma, that's 30. So we've got a problem involving means. Sigma is known, so we're going to be using the Z distribution. The other thing I like to just sort of think about while I'm reading through a question before I get into the working is whether or not there's any reference to direction in the wording of the question. So we're wanting to test here whether the mean withdrawal amount is no longer $160. We have not specified a direction. We haven't said we want to see if it's more than $160. We haven't said we want to see if it's less than $160. Just that it's no longer $160. So that tells me it's going to be a two-tailed test. Equals, not equals. We're not interested in direction, just if it's different. So I'll start setting everything up. The null is that mu is equal to 160. The null hypothesis, our status quo, is that the population mean is equal to 160. In the alternative, it's that mu, our population mean, is not 160. So it's equals, not equals, because direction is not relevant. We just want to see if it's no longer $160. Alpha is 5%. I know it's a two-tailed test, so I'll draw up my decision diagram. Now we've already established up the top that if we're dealing with means and sigma is known, so if we know population standard deviation, as we do here, it's the normal Z distribution. So I draw my Z decision diagram. It's two-tail, so I have two rejection regions. I can shade those in, a lower tail reject region and an upper tail reject region. Whenever it's two-tail, well, alpha still represents the entire reject region area. So if the entire reject region area is 5% and it's a two-tail test, that 5% is split over the two reject regions. So I've got 2.5% in the lower reject region and 2.5% in the upper reject region. Once I've established that and drawn up my diagram, I can go to the inverse Z table and look up the upper tail cutoff point. So that's what I can get from an inverse Z table. If I look up 2.5% as my alpha value, so the area, and I change it to a decimal, so 0.025, the cutoff point, the Z value that goes with an area of 2.5%, is 1.96. So that's my critical value for the upper reject region. The great thing about Z is it's symmetrical. So once I've got the upper critical value, that upper cutoff point for the reject region, to get the lower reject region cutoff point, it's just the negative of the same number. So the lower reject region has a cutoff of 1.96 negative. So that is my decision diagram. I've got the information using the inverse Z table. From there, I can look at calculating the test statistic. Now remember, the test statistic is where we take our sample that we're going to use as evidence, and basically we convert it into an equivalent Z-score so we can compare it to our decision diagram. So we had a sample mean of 172, and that was for a sample size of 36. So we've got X bar, we've got N, and we just need to convert that into a Z value. That's our test statistic. So the test statistic formula is our point estimate X bar minus mu, our hypothesized mean, divided by standard error, and in this case standard error is sigma over the square root of n. Remember, when sigma is known, you can use it. So X bar is 172, put that in. Mu, well, you put in the value for mu as if the null is true. So hypothesis tests proceed on the basis that the null hypothesis is true. So that's like saying mu is equal to 160, so substitute that into the test statistic equation. Then divide by our standard error, which is going to be population standard deviation of 30, divide by the square root of 36. Put that into your calculator and our test statistic comes out at 2.40. If we look at our test statistic and compare it to our decision diagram, 2.40 is in the upper tail reject region. The cutoff point was 1.96, so anything greater than 1.96 would mean that we reject the null hypothesis. 2.4 is definitely in that upper tail reject region, so our initial conclusion is to reject the null at alpha of 5%. Remember, we don't stop there, we write the conclusion firstly in terms of the null, so reject the null, but then we must reinterpret that in relation to the alternative hypothesis. So by rejecting the null, what we're really saying is there is enough evidence to conclude that the mean amount of cash withdrawn per customer from the ATM is not equal to 160. Remember, we haven't specified direction, so the sample evidence is allowing us to reject the null, and in doing that we're saying that our mean withdrawal amount is not equal to 160. It's different to 160. If we wanted to test to see if it's more or less, from the sample it looks like it's possibly more, well, that would be a different test. That would be a one-tail test. For this situation, that's our conclusion.